Good morning.
Hello.
How's your piano lessons coming?
You're talking to me.
Yes.
What was your question?
How are your piano lessons
Oh,
coming?
piano. Well, right now I can't find a teacher that I is available and has the same interest that I do. I For a while I was getting lessons from my grandson's school music teacher who has the background I like, but then very inconveniently his wife had a baby and he's on paternity leave. So if you know somebody, tell them to call me because I definitely need
Remember
help.
when you started your first lesson?
I didn't I stepped on you. What did you say? What first
I
lesson?
said, I remember when you started your first lesson.
Uh, Really?
Yeah.
How long ago was that?
Well, you didn't stay long for class after it was over.
Oh, okay. Well, I'm happy to report that I managed to get into this Zoom without having to struggle. I don't,
Hmm.
sometimes I have issues. I've been doing this for a long time and uh, sometimes this doesn't work easily. Anyway, we're here and I'm going to wait till 9:30 before we get started. While we're waiting, you can ponder this piece of artwork that shows a primitive being looking at something even more primitive. And the reason I use this piece of artwork is it's kind of like where physics is today, physics being the monkey and quantum mechanics being this object that defies
A thinker
uh,
monkey.
understanding. So,
A thinker monkey. Oh, it's monkeys.
yeah, an interesting piece of art I found. Today, I'm going to do the layout a little differently. I'm going to do two pages side by side. I hope that's going to work for people because there's so much going on in today's presentation that I need to be able to um, see what's coming up.
Good morning, Ed.
Good morning. Uh, okay, we're getting close here, and I had the screen the way I wanted it, and I seem to have
That up.
screened it what I want. Let's do this. Stop sharing and okay, and then Okay, so you should see 2 pages side by side. Is that what you're seeing?
Yes.
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 All right, well, it's 9:30. Before I make any more mistakes, let's get started. So today we're going to dive into the deep end of the pool in the sense that in prior weeks, we've come to understand the foundations, a history of quantum mechanics, how it evolved from primitive ideas at the end of the 19th century, and then the emergence of the first generation of quantum concepts, including Niels Bohr's very successful model of hydrogen. Last week, we talked about how that idea was set aside and a whole new idea based on Schrodinger's equation, wave functions, all that sort of thing was covered last week. And you'd think we'd be satisfied, but we're not. Because almost immediately, criticisms emerged and deep questions popped up in a way that questions that were never had to be asked in the prior development of physics, starting with Newton and the astronomers who were making detailed measurements of the motions of the planets and so forth. These new questions that emerged digging into quantum mechanics is the subject of today's presentation. And you see here the outline. And it's going to take this lecture and 2 more to tease out what's really going on here. So we do have a summary of what we've covered in lectures 1 through 3. And I'll just remind you that we've talked quite a bit about wave-particle duality, a whole new concept that doesn't appear in classical physics. The idea that a quantum state can exhibit something called superposition, that is, it can have multiple states. Remember, I used the concept of a platypus to try to illustrate this, where a quantum system can exhibit behavior of multiple different versions of that system all at the same time. Then we have this totally bizarre thing, entanglement, and we'll talk about that quite a bit today. We have the uncertainty principle, and I'm going to explain to you or remind you that last time we talked about how this has an analogy to the way optical systems work, that you can design a perfect system with lenses and mirrors, but you can never achieve perfect focus because you're dealing with waves. And indeed, Schrodinger's description of quantum mechanics is all about waves. Now, we've also talked about quantum tunneling, where objects can appear to pop through a barrier. We're going to talk today about decoherence, so I'm going to skip that. We also learned that quantum science, for the first time, violates the laws of cause and effect, that things happen in quantum systems without any apparent cause, like the decomposition of a radioactive nucleus just happens randomly. There's no way to predict when that's going to happen. We're going to reiterate issues with the measurement problem and additional topics. So we had, in the evolution of quantum mechanics, by the time 1925 rolled around,
Tryons or stuff.
yeah, go on mute if you're not asking a question, because I don't want to miss questions and we don't want to get distracted. So by 1925, we had Schrodinger's equation. People started using it and all sorts of interesting results were achieved. And Einstein was troubled by the implications of the new version of quantum mechanics that existed by roughly 1925. I mean, he was set aside anything you've heard about him not understanding quantum mechanics. Far from it. He was a founding member of the community that created the theory, and he had deep insight into why the description of the atomic world and the subatomic world was not consistent with all prior physics. And we're going to hear about this over and over as we progress through today's presentation. So here are these kind of artistic, primitive artistic stuff done by me about properties of the quantum world. This all comes from a piece of art I showed you back in the first lecture. But there are two things here I want to emphasize. I want to have a new conversation about this double slit business. Remember the history that Thomas Young in the very early 1800s demonstrated the wave-like behavior of light. If you have a light source and two slits, you get these spots, multiple spots of light that you would not normally expect. These are called fringes, and this is indicative of wave-like behavior. One thing I mentioned in the first lecture, but now I want to emphasize again, we can do this experiment with any type of quantum particle. We can do it with light, we can do it with electrons, we can do it with complex molecules, and so forth. What I want to emphasize now is if we block one of these openings so that we know that the quantum particle has gone through this slit, at that point, we do not get this kind of behavior. We do not see fringes. And the idea that we are learning the trajectory of a quantum particle, for example, if we redid this experiment with electrons, and we have an electron source here, and we let the electrons fall on these two slits, we will get this kind of fringe pattern indicating that something wave-like associated with those electrons is encountering the two slits. But if we cover up one of the slits, you do not get this pattern. And the way we think about this is if we have which way information, I'm saying which way with little quotes around it, if we know that by covering this slit, we know that the electron went through here, we do not see this interference pattern or the fringes. And if we cover this one, and we know the electron went through here, we don't see fringes. This has aroused at the time early questions about, is it what we know about the quantum system that dictates the behavior of an experiment? Or is this odd wave-like behavior the way nature functions? So the issue came up as early as 1925, 27. Is it about the observer? Is there something about having instrumentation that allows us to observe this pattern? Is that's what is dictating this issue of knowing which way a quantum particle goes through double slits? So this is going to come up. I thought I'd mention it again so I remind you of some of the vocabulary. Here in this small panel, we have this issue about the interpretation of why early in an experiment, we have a wave function that predicts the outcome of an experiment. And then if we're right here, we make a measurement, we actually have a specific value that results. And what happened to the wave function? The wave function is a mathematical entity. It extends through the entire universe. And suddenly it disappears when we make a measurement. This is the so-called collapse of the wave function. This was an immediate point of criticism when people had the time to think about what does the Schrodinger equation tell us about the atomic and subatomic world. Now, unfortunately, because of my jury duty obligation, I did not get a chance to speak to you live about the Stern-Gerlach experiment. It is on a video that I hope that you used in place of me when I missed 2 weeks ago. But Stern-Gerlach experiment has this, let me review it so you can ask questions if you need to. And let me do a little thing here so I can make this bigger.
Thank you.
Yeah, I'll jump in and out of this during the lecture. As I said, the reason I'm showing 2 pages at once is there's a lot of material in today's presentation, and I have to be able to see ahead when I'm talking about a topic, so I see what's coming and can form a context for you. So let's talk about the Stern-Gerlach experiment. This is from 1923. And it's a brilliant piece of scientific instrumentation. What Stern conjured up and had Gerlach build for him is a test of the magnetic properties of atoms, which was an unknown entity. I mean, the concept of atoms having magnetic properties was not understood in the early 1920s. But this experiment illuminated a whole new area of how to think about the reality of what goes on in the atomic world. So let me describe this to you. We have an oven here, and it has silver in it. And as a result of heating the silver up, we get a beam of silver atoms that goes through a couple of little holes to form a nice clean beam here. The beam of atoms then encounters this set of magnets, one marked north, one marked south, and you see the North Pole comes to a point. This channel, therefore, has an intense magnetic field all along this path for the beam. And between the South Pole and the North Pole, this side, the North Pole, has a more intense magnetic field. And the expectation that Stern had was, when I turn this oven on and pass the atoms through this magnetic thing, I'll get a smear of hits on a target where the atoms collect. Because the atoms come out of this oven in all kinds of random orientations. Imagine just having a bunch of, for example, tennis balls, each having half of it painted black. And you had a steady stream of these tennis balls flying through the air. The orientation of each of those tennis balls would be random. But that's not what they got. They got 2 spots, here, and nothing in between. And this was a mystery. Fortunately, and this happened a lot in quantum mechanics, almost the same time, people not associated with this experiment had come up with the concept that all quanta have magnetic properties. So the idea that a atom could behave like a magnet that you might put on your refrigerator, that it has a North Pole and a South Pole. It took a while for that idea to come in contact with the results of Stern and Gerlach. And people realized that the random atoms coming out of the oven encountering this magnet could be oriented only one of two ways. A way that produced this spot and the opposite, sort of the flipping over of the atom that illuminated this spot. And this idea of quantized magnetic properties added to the theory and the concern about how we interpret the quantum world. Because again, the expectation was we just get a smooth pile of back this up. So keep that in mind, that the Stern-Gerlach experiment added information about the behavior of atomic and subatomic particles, but at the same time, it raised questions about why is it that we only get two spots, one there and one there. Okay. Another fortunate occurrence was this, the Solvay Conference of 1927. Solvay was a rich industrialist who was sort of an amateur scientist, and he spent money. His family is still spending money. There are still Solvay conferences. And in 1927, they held a conference in Brussels and invited all the leading thinkers about quantum mechanics. But because by 1927, the success of the Schrödinger equation in describing atomic phenomena had been proven over and over again. But the understanding of why it works and works so well had not kept up. And so we have here the leading thinkers. Here's Max Planck, who was really the first quantum scientist, Madame Curie, Einstein, Schrödinger, Paul Dirac, Heisenberg, Wolfgang Pauli, and so forth. So they have this conference. And like most conferences, most of the work got done in the hallways and the restaurants in the vicinity of the conference hall, where arguments were made and debated about what it is that the quantum world is doing. And Einstein came with thought experiments, Gedanken experiments, and you'll see that word, big, long German word, will pop up here occasionally. And he came full of criticism about why it is that Schrödinger's approach, the uncertainty principle, and all the other tools that had been invented in the prior 5 years or so, why those things worked. And the central issue was the debate between Bohr and Einstein. This is the beginning of a decades-long conversation. You can call it a conversation, or you could call it an argument between Bohr and Einstein, each equipped with deep understanding of the quantum physics, but their interpretation of what was happening was very different. And to sum it up succinctly, Bohr was content with the version of quantum mechanics that existed in 1925. He felt like any effort to understand what the quantum world is doing is a waste of time. Indeed, you can find quotes where he said, "There is no quantum world until we make a measurement," that there's no reason to ponder what it is that those electrons are doing. Or, for example, when we go back to the double slit experiment here, there's no reason to worry why, if we cover up one of these slits, we suddenly lose this wave-like behavior that had been observed and predicted and observed. Einstein, on the other hand, said, if quantum mechanics is right, then there are certain consequences that we should see in the physical world, and we don't see those consequences. He thought that the description, as successful as it was, of the atomic and subatomic world was incomplete. And he had lots of arguments to try to make his point. So let's slide down here. And again, I'm going to focus in on this. Einstein came to Solvay, 1927, and said, the uncertainty principle cannot be right. Remember, this is Heisenberg's idea that there's a limit to how well we can measure a quantum system. And here's Einstein's thought experiment, the so-called Gedanken experiment. And he said, suppose we do a double slit experiment, just like we showed on the previous page with electrons. We shoot one electron at a time into this experiment. We don't know where the electron is going to encounter. We don't know which of these slits the electron is going to encounter. But if we have the two slits open, we will see the fringes that I illustrated on the previous page. And indeed, it took decades to do this experiment, but it has been done, and the predictions of quantum mechanics are that we would see fringes with electrons. His argument was, when the electron encounters the screen, it must, in order for it to change direction, you see this line is going along, the electron's going along, and then it changes direction. Or if it goes through this one, it changes direction. And if it's a wave, both parts of the wave that encounter the slits change direction. That must influence the screen. Something bumped into the screen. And he has this idea that the screen is hanging from a spring, and we have a very carefully designed measurement device to measure anything that disturbs the screen. And his argument was, if I can measure the motion of the screen that happens as a single electron flies from the electron gun, and I measure where that electron hits the screen. Remember, it takes many electrons to form the fringe pattern, but if you do it one electron at a time, you get one spot at a time. And I remember I showed you last week, an accumulation of those spots eventually shows the property of fringes. So he said, well, I know exactly where the electron ended up. That tells me the position of the electron. And this display, what he called a displacement meter, tells me how much interaction occurred between the electron and this screen. Then I'm simultaneously measuring the position and momentum of these quanta particles, in this case, electrons. And that violates the uncertainty principle. And whoops, what happened? Hang on. We were doing so well. I don't know. Drat. All right, I have to do it this way. Stop sharing. I apologize. I don't know what I did. Oh, maybe if I do this. Oh, I made the page so big that we couldn't see it. Okay. So we're back. I'll resume sharing in just as soon as I get my wits about me.
Well,
Almost there.
being kind matters, yeah. Well, there's two things.
There we go.
Be
You should be seeing the screen now. Okay. So he raised this question, and basically threw this at Bohr and said, go ahead, explain how quantum mechanics actually doesn't have an uncertainty principle, because I can measure the position of an electron striking the screen, and I can measure the momentum it imparted to the screen in order to have the electron interact with the screen.
We're not seeing your screen right now.
Oh, ooh-wee. Here we go. Cancel that. You're not seeing the screen. Stop sharing. Share. That. Why is that? Oh, how about this?
Yes, that looks good.
Thank you. Sorry for the interruption. So Einstein threw this at Bohr, and Bohr said, I know what's going on. If you try to measure the position of the impulse of the electrons interacting with the screen, and you know perfectly well where the electrons arrive, you can do that. But if you make the measurement with this position sensor, you will, if you make the position sensor very, very accurate, the fringes will be less profound. Instead of seeing nice blobs of light like this, you would see much less distinct fringes. And the more precisely you measure the motion of the screen, the less precise these fringes will be. And the community that witnessed the debate agreed, yeah, Bohr is right. We'll see less and less fringing if you measure if you measure the screen very precisely. And so Einstein went away defeated, but not done. And he came back later with another idea. Can you see it's almost the same kind of thing? He imagined a box with a clock and a door, and occasionally the door would open and light from inside the box could leave, and somewhere else we measure the properties of that photon of light that managed to come out while the door was open. And the properties of the photon, the energy of the photon, could be precisely measured. You just have a camera over here somewhere measuring it. And because you have an ultra precise clock, you would know exactly when the photon left. And one of the versions of the uncertainty principle is that precise measurement of energy and time of the same object cannot be as precise as you desire. There's a limit imposed by the uncertainty principle. And he threw this at Niels Bohr. And Bohr was shocked. In fact, you see one of the witnesses, Rosenfeld, said it was a real shock for Bohr to have to think about this ingenious experiment that Einstein had conjured up. And Bohr went back to his room and thought about it. And in the morning, he came in with the answer. What he realized was this whole apparatus is hanging from this spring, and the position of the box is indicated by this scale. But Einstein's own theory of relativity says that in a changing gravitational field, the rate at which clocks progress changes. And the idea here is if the photon that we imagine leaves the box when the door is open, the energy in the box is reduced, which means in a microscopic way, the spring gets a little shorter. And if the spring gets a little shorter, the whole apparatus is now in a different gravitational field than when we started the experiment. which means the rate at which the clock is measuring time is altered.
No.
And if you go through the arithmetic, which Bohr did overnight, you find that the uncertainty principle applies to this experiment. So we have these, hang on, I'm having a new problem now. I want to make this whole thing smaller. Oh, good grief. That the upshot is Einstein was defeated in his attempts to undermine or point out weaknesses in the behavior of quantum mechanical systems. And this debate, at that point, Einstein gave up. In fact, he said, in effect, I give up. This is 1927. I give up. I've got to think about this and figure out how to portray my lack of confidence in quantum mechanics. And it took another 8 years for him to come back to the community, not at a conference, but rather in the form of a paper, a professionally edited paper that we will talk about here in a second. So, in summary, as I wrote here, Einstein became quiet and he retreated from the debate until 1935. Now, some of you know about Schrodinger's cat. There's a little diversion to help illustrate what we're worried about. You know about Schrodinger's cat. We put a cat in a box. There's the cat. The cat is in a box with some kind of radioactive material. And a Geiger counter, which detects radioactivity, is connected to, in the original form of this experiment, a vial of poison that will kill the cat if an atomic event occurs, namely radioactivity comes out of the radioactive material, hits the Geiger counter, which is connected to a little hammer. The hammer breaks the vial of poison and the cat is dead. Now the question is, if you look in the box, do you see an alive or dead cat? Is the cat dead or alive before you intrude and look in the box to find out what's going on? Now, this is a famous concept developed by Schrodinger to try to point out the inconsistency of quantum mechanics, something he invented, the inconsistency of that kind of science with our observations of the real world. And for decades, this was an open question about, is the cat dead or alive, before you open the box to make the observation. This touches on a point I made a few minutes ago. What is the role of the observer in quantum mechanics? This is still a topic of debate. And it, off and on over the last 100 years, it's been argued on both sides that quantum mechanics functions even if there are not observers. And on the other hand, the idea that it's preposterous to think that we need an observer for a quantum mechanical system to function. In fact, one of the arguments is the universe is filled with quantum mechanical things going on all the time. Stars produce light using quantum mechanical phenomena. How is it that there's no observer at the sun watching all those things happen, but we are here to observe it? And the argument's been made by scientific philosophers, if we weren't here to make the observation, there would be no such stellar activity. Finally, we have, in the last 20 years, some enlightenment about this, which I've tried to capture in this little box. I'm actually going to edit the book to capture this idea, and it's something I mentioned right at the beginning of this presentation. It's the idea of decoherence. What in the world is that? Decoherence says a quantum system can only retain its quantum behavior, that is, be described by a wave function that comports with Schrodinger's equation, that can only happen if the quantum system is isolated from the broader macroscopic world, the world we occupy, the world of trees and streets and atoms, not atoms, but stars and so forth. And the argument now is that the idea that a cat can be sitting in a box in a superposition, right there, superposition of both dead and alive is not what's going on, because the cat is in contact with the box, the air in the box, sound waves coming in and out of the box, and so forth, and that the quantum behavior that you expect to see is set aside because the cat interacts with the broader environment. And that interaction with broader environment is called decoherence. And understanding this has been critical to the development of quantum computers, because in order to make a quantum computer do what it does, the atomic and subatomic things that must go on in a quantum computer have to be carefully isolated from their environment. So the strange business of the cat in the box is now deemed as a non-issue because of this idea of decoherence. And there's more about this here. I'm not going to go over it right now, having to do with who the observers are. I'll let you read that. So, in summary, by 1927, Einstein had thrown several experimental ideas at principally at Niels Bohr, and said, tell me how it's possible that quantum mechanics is successful in describing the atomic and subatomic world. We can use it for all kinds of things. We can build the periodic table of elements in a way that no one has ever been able to do before. He anticipated all sorts of additional advances like transistors and lasers and things that we now have built. He said, how is that theory so successful, and yet it violates our understanding of the physical world based on hundreds of years of science? And so his criticism silenced after 1927, but now we go to 1935. Among other things, of course, there was the beginning of and the consequence of World War II was imposing its will on mostly European scientists who had to leave Europe. Most did, including Einstein. He left and he never went back. And the debate he had with Bohr was quiet, but he was thinking about this issue of what's really going on in quantum mechanics. And by 1935, he engaged the help of two colleagues, Podolsky and Rosen, and together they wrote a paper challenging the fundamental precepts of quantum mechanics, that because they had deep questions about several topics, we're going to go into those in a minute. The paper was an earthquake in physics. People read it and realized that there are these fundamental questions that haven't been answered, and the giant Einstein is leading the charge to ask what is missing from quantum mechanics. It works, but there must be some part of it that is invisible to us. And I'll introduce the language that they used in a second. So the paper came out in 1935, and it proposed an experiment yet another experiment that was the key to how they criticized quantum mechanics. And by the way, here's 1935. There was a little bump in interest. I mean, at that time, there weren't very many physicists, and most of them, the European ones, were running for their lives. And so there was a flurry of activity. These are the number of professional papers citing the paper Einstein, Podolsky, and Rosen wrote. So it was a bump in interest, and then it died away until the 1970s. And you can see now, that paper is everywhere. It's very prominent. And the interesting thing is that resolution of the issues in their criticism of quantum mechanics has been completed. Experiments have been conducted that could not have been done in 1935. And the results of those experiments resolve his concerns, his criticisms, in a way that Einstein would have liked least. And I'll get into that detail here in a second. So for a while, there was a buzz. And of course, right there is World War II. But now everybody reads that paper to understand how Einstein went wrong. Here's the new thought experiment. Let's see if I have a picture of it in a second. So basically, we have our friends, Alice and Bob. Remember, I introduced those some time ago. And in this box, I'll describe what they're doing. By some atomic process, we create entangled particles. Up to 1935, this was an odd feature of quantum mechanics that had been pointed out by Schrödinger, that under the right circumstances, two particles could be created that are linked in an invisible way, as I discussed last week. That if you measure one of them, the other one would have to effectively be forced to exhibit a companion result. That is, if one, let's say we have in some atomic process, we produce two photons, puffs of light. And each of those photons has some feature, well, I will call up and down. It's either up or down, just like from the Stern-Gerlach experiment with atoms. The photon either has an up orientation or a down orientation. In the process that Einstein imagined and that Schrödinger showed with mathematics could happen, entangled particles would be such that one of the particles would be up, the other would have to have the property of being oriented down. And they fly away from each other, and Alice and Bob measure. Here's Alice and Bob. Alice and Bob have equipment to measure the orientation of the photons they get. And you do this one experiment at a time. So at any one instant, there's one photon heading to Alice and one heading to Bob. And they use their laboratory equipment to measure these orientations. And if Bob measures an up, we know that Alice must measure a down orientation for her photon. And Einstein and Podolsky and Rosen's argument was, how does Alice's photon know which way to be oriented when it arrives at her equipment? They argued there must be something in the process of creating entangled particles that endows Bob's photon with knowledge of what Alice is going to get. This endowment of knowledge about what's going to happen some other place in the universe was offensive to Einstein, particularly when you can imagine we would do this experiment over such huge distances that when Alice gets her photon and measures it, the photon going to Bob may still not have gotten to him because the experimenters don't have to be the same distance from the device that produced the two photons. So the argument of Einstein, Podolsky, and Rosen, which I'll abbreviate as EPR from now on, EPR said, how is it possible that far distant scientists, each receiving a photon, would get correlated results unless, unbeknownst to them, each of their photons has knowledge of what is going to happen in the future when the two photons are detected. All of this was offensive to EPR, and their argument was there must be other information conveyed with those two photons, the one for Alice and the one for Bob, and they called those hidden variables or hidden information. And for a long time, from 1935 until real measurements were done in the early 1970s, that concern pervaded the physics community. How is it that there aren't sources of information that tell the equipment that Bob uses what measurement result he has to get so that it's correlated with Alice's result? There was no explanation until roughly the 1955 or so. So here are the complaints summarized. Einstein, or the EPR guys, were offended by the violation of locality that this implies. This experiment says, no matter how far apart Alice and Bob are, some kind of signal, something must connect the particles A and B. And that violates Einstein's theory of relativity, where somehow a signal from Alice's equipment could get to Bob in spite of the fact that he could be so far away that light couldn't make that trip in time to influence Bob's result. That immediately leads to the idea that there are hidden variables, hidden information that must be embedded in those photons. They're invisibly tiny little puffs of energy. How is that possible? And I include this picture from the movie The Wizard of Oz, which explains the mysterious stuff that happens in the movie because there's a guy behind the curtain controlling everything. And this is where Einstein's thinking was. There must be something more to quantum mechanics for it to produce the results it produces, but we do not have a description of that hidden information. And that's when this idea, I don't think Einstein used this term, but it's the common term used today to describe the challenge that Einstein threw out there. There must be hidden variables so that results of these kinds of experiments could be correlated. So there's more for you to read there about this. And let's move forward. So in 1935, the paper, which is, even in Einstein's opinion, unnecessarily complicated. He did not write the paper. Rosen, I believe it was Rosen, wrote the paper in English because he had English was possibly his native language. In any case, the paper is unnecessarily complex, and so I offer you this idea here. If you want to understand the EPR paper, don't read the original. Read the modern interpretations of it, which I've tried to summarize for you, and I will show you my summary in a second. But here's what Einstein said. He said that what happens at B should not depend on what is measured at A. He was arguing that the prediction of quantum mechanics that can be entanglement cannot be truthful. That was his argument. And he goes on in this little paragraph to explain his complaint. Now, a big breakthrough came in 1951 when David Bohm, who was a young professor at Princeton at the time, he came up with a better way to implement the experiment that Einstein, Podolsky, and Rosen had originally created. I'm not going to go into the technical reason, but Bohm was the one in a physics book that he wrote in the early 50s. He came up with a better, cleaner way to imagine the experiment. And that's the one I described to you a minute ago, the use of light particles, photons, to do the experiment. That was not the original description of the experiment provided by Einstein and his colleagues. So Bohm, incidentally, introduced his idea for a better way to think about the experiment while he was as I say, a junior professor in Princeton, and Einstein was there in Princeton, and they got together. Einstein read Bohm's book on quantum mechanics, and in a series of meetings told Bohm that Bohm had written the best possible description of quantum mechanics as it existed at the time, but it was still defective because it didn't explain a resolution to this EPR challenge that Einstein and his colleagues proposed. And Bohm realized Einstein is right. There has to be a different way to think about this. And in the lecture 6, we'll talk about Bohm's new idea for how to think about quantum mechanics, but that comes later. So Bohm has this idea for a better way to do the experiment, and it opened the door 10 years later to actual development of laboratory approaches to making measurements that could prove or disprove Einstein's claims that there must be hidden variables. There must be hidden information in quantum mechanics for it to behave the way it does. So to reiterate, here's the experiment that you might conjure up using Bohm's approach. We have a light source here. Here's Bob, and there's Alice off in the distance, and they are different distances from this source. And the experiment they conduct is that every once in a while, somebody pushes a button and entangled photons are created in this box, one going to Bob and one going to Alice. And each of our experimenters make measurements. And when they're done, they can correlate the results they get. If Bob gets a up photon, Alice gets a down, and vice versa. And you just keep doing this. And the good news is that by the early 1970s, experimenters had figured out how to produce entangled pairs of photons. When Einstein and his colleagues wrote their paper, there was no such technique for doing this. But using quantum mechanics, experimenters figured out how to make entangled pairs of photons. And now the idea was you could actually do the experiment and see if the following complaints that Einstein had were worthy. Remember, he was complaining about locality. That is, that somehow information was conveyed between Alice and Bob faster than the speed of light. Second, do you need hidden variables to make sure that the correlation between the two experimenters is real? These are the two principal complaints that Einstein had. So by the early 1970s, the possibility existed to build an experiment. And indeed, somebody did. And let me just tell you the mood of science, or particularly physics at the time, when the first idea to actually measure the properties of separated experimenters using entangled particles, when that first idea came to mind to a guy named John Clauser, his colleagues and the funding agency that he had said, "We're not paying for that. That's not physics. It's some kind of argument should be held in the philosophy department of what it is that happens in the atomic and subatomic world when we do experiments." Meanwhile, the influence of Niels Bohr arguing that we don't have to worry about what's really going on. Let's just go in the laboratory and make discoveries and use those discoveries for the benefit of mankind and not worry about the exact intricacies of what quantum things are going on. But Clauser, with a help from a few influential friends and access to a warehouse of discarded equipment, built an experiment just like what I've sketched in this cartoon. And so Clauser and his student, named Friedman, spelled different, not related to me, built the first experiment to test whether the EPR experiment is an accurate description of the way the world works. So we're close to a break, and I think this would be a good opportunity to take a break, and I'll come back. Well, wait, one thing. Let's take a look at the chats. These are all administrative things. Oh, wait, there is a technical question here. From Tricia, yes. Okay, we're talking about Stern and Gerlach, and this is an important question that Tricia has asked. To do experiments on the magnetic properties of atoms, the first thought is to have the beam go through a uniform magnetic field, just kind of the thing that a refrigerator magnet produces. And Stern quickly realized that's not going to actually test the magnetic properties of silver atoms coming out of an oven. And he and his collaborator figured out we need a magnetic field. Let's go back real quickly. Don't get dizzy. Let's go back to that picture of the Stern-Gerlach experiment. It's right here. Whoops. Where did it go? Okay. I moved too fast. There it is. Their idea was to make the magnetic field non-uniform. That is, let's get this out of the way. By bringing this magnet to a sharp point and having a groove here, means the magnetic field is not uniform, and the atoms, each atom on its trajectory would interact with a larger force here and a lesser force there, and that could produce, they expected, this result. And as I pointed out, they didn't get that. They got this. They got atoms with a magnetic property pointing up and a separate one for pointing down. And this was influential in thinking about how to do these kinds of experiments. I'm wondering if I actually answered your question adequately, Tricia. If I didn't, let me know and we can try another approach. But for now, let's take our break.
I
Before
think, I think adequate is a relative term when we're talking about quantum mechanics, don't you?
yes, yes. But to measure, let me try to be real succinct. To measure the magnetic properties of silver atoms, you need to use magnets.
Ed, this is Janice. I have a question.
Yeah, go right ahead.
Okay, remember that I'm a real novice in this. So,
Aren't we
what's
all?
been bothering me all week was what is the real definition of spin? What does that mean?
Ah, excellent, excellent. So let me tell you that the invention of spin by two students in 1923, almost identically at the time that Stern and Gerlach were doing their experiments, unbeknownst to them, there were two students in Denmark who thought about the spectra of hydrogen, the spectrum of hydrogen. And they saw in what was then the modern investigation of the colors that come from hydrogen, that there was hidden in there some detail that had not been seen before. Earlier experimenters back in the 1870s and 1880s had seen colors coming. Remember, I showed those tubes of hydrogen that you run an electric current through, and it glows. And if you study the glow, you see different colors. But the two students realized there's more detail in there that has not been explained, and they conjured up the idea that the electron, the single electron in hydrogen, could have one of two orientations in the hydrogen atom, up or down. And because the electron is a charged particle, they said this must be a magnetic property because it was already known that moving electric charge creates magnetism. When you start your car, electric current from the battery goes through an electric motor that relies on this concept that moving electric charge creates magnetic force. And so the two students, Uhlenbeck and Gaudsmit, went to their professor and said, we think electrons have magnetism. And it comes from the fact that the electrons are spinning. They imagined the electron was like a little a top that your grandchild might play with. You spin it, and if it's a charged particle, that spinning process would create magnetism, which could explain the spectrum of hydrogen that Uhlenbeck and Gaudsmit knew about. And so the idea that a subatomic particle like an electron having a magnetic field must result from spin. That came into the vernacular, and in chapter 1, if you look, there's a footnote there where I explain that nothing is spinning. We now know nothing is spinning, but the connection between electric charge and magnetic properties implied to the generation of physicists 100 years ago, something is spinning, physically spinning, but that's not true. Almost all subatomic particles have magnetic properties, and nothing is rotating. They just are born that way. And we have to accept that. See, I'm behaving now, to be serious, I'm behaving like Niels Bohr, who said, don't look too deeply into these questions. You don't need to. We know that electrons have magnetic properties, and don't worry about whether the electron is spinning or not. You'll just get sad and start crying. Did that help? Hello?
Yes, thank you.
You now know as much about the connection between spin and magnetism as anybody else on Earth. because there's no explanation for why an electron has magnetic and other atomic and subatomic particles have magnetic properties. There's no reason that should happen, but there it is. All right, let's see. I have one more quote and then we'll take our break. Don't forget to mute. Haha, spin. Okay, so let's take a little break. It's now 10:35. We'll come back at 10:40 for more of the insanity of quantum mechanics. All right, we've had our little break. It's 10:40, and now we're going to enter the modern interpretation of how to explain what quantum mechanics is doing. The modern interpretation isn't a single thought about what the dynamics of quantum mechanics is. It's a family of ideas, and we'll go over these more and more as we continue through the rest of the class. But the beginning of the modern thought is the result of John Bell, an Irish physicist who had a deep commitment to intellectual honesty and had, as a result, many arguments with his professors when he was in school about what is quantum mechanics really telling us. And he was a pest. He kept asking, and the professors kept saying, stop asking me. The professors, this was in the early 50s, professors all adopting the Niels Bohr approach of don't ask me about what's happening down there in the details of atoms. Just learn how to work with the Schrodinger equation and other tools to be able to describe the physical world and design experiments and continue to gain more knowledge. But stop asking me why it works that way. But Bell was persistent, and as soon as he established himself as a working scientist, he began spending his Sundays. You see here this quote. On Sundays, I have principles, meaning that on the weekends, instead of worrying about his everyday, day-to-day job of designing accelerators for doing subatomic physics, he thought about what the EPR paper had brought up and began looking for ideas of how to resolve this issue. I remember now we're now 30 years after, in mid 60s, 30 years after the EPR paper came out, and little attention had been paid to it. But Bell persisted and thought about ways to do experiments, and he knew of Bohm's idea for using the spin of photons to do the experiment that had been thought up by Einstein, but could not be done in Einstein's day. And the question was, could we determine if quantum mechanics is a local phenomenon? Meaning, if we have entangled particles, does quantum mechanics ignore the rules of relativity and send signals from Alice to Bob or vice versa so that the results they get from their experiments are correlated no matter how far apart they are? And by the way, something I forgot to say, let's go back to this. When you design these experiments, I can put Alice farther away from the source of the entangled particles. But the question remains, who makes the measurement first? Because there was this idea, well, if Bob makes the measurement first, then somehow information about his results get conveyed to Alice's equipment and influences Alice's results so that there's correlation between the two results. But Bob doesn't know if he's the first one to make a measurement. For all he knows, the source is way over here. And relativity adds to this because in relativistic environments, for example, if Bob is moving with respect to Alice, it's impossible to detect which one of them takes action first. So there's more text here you can read about that. So Bell kept thinking about experiments that might be done to resolve the EPR dilemma. And in fact, hang on. By employing logic that doesn't have to do with quantum mechanics, by thinking clearly about what's going on in these experiments, he managed to show that there are results that can be obtained if you build the experiment correctly. And in fact, I have an appendix to the book that has a very simple example of how to apply Bell's logic, the so-called Bell's theorem, to a problem that has nothing to do with science. And I'll leave it to you to read that if you want. So here's an example of the correlation we've been talking about. When Alice gets a result of -1, Bob has to get a result of 1. And the correlation is perfect in this imagined case. And so Bell's theorem comes from understanding what the EPR paper was trying to do, from understanding what Bohm had proposed as an experimental approach, and to put those together in a way that, as we see here, figure out a way to do an experiment that could be tested in a laboratory. And I've already told you that the central point of doing these experiments is to be able to create entangled particles. These are particles that we now know have some connection that we cannot detect. And it doesn't matter how far apart they are. And in retrospect, we find that this person, a Chinese woman who was at Columbia University in the early 50s, actually was the first, she and her student were the first to detect entangled particles. It's probably, you can read the different history books on this, it's probable that she and her student did not realize that they were detecting entangled particles in the radioactivity experiments they were conducting in the early 1950s. But they could see energetic particles coming out of a radioactive source 2 at a time. And as I say, in retrospect, that was probably the first detection of something that Schrodinger had predicted in 1935, that the equations of quantum mechanics said to him, in the right circumstance, we can produce 2 identical particles, twins, if you will, and they're entangled forever until one of them or the other gets measured, at which point one of the particles has disappeared into an experiment or into a natural phenomenon, and the entanglement ends at that point. So Madame Wu was doing her work, and Bohm, who we already met, realized years later that they were doing entangled particles. And the question was, could a convenient, safe source, non-radioactive source, be created to reliably produce pairs of entangled particles? And by the early 1970s, that was made possible. And the way you do that, and it's done now, but undergraduates do this all the time, you have a special crystal that has the property that if you illuminate it with ultraviolet light, occasionally you get 2 photons that are entangled. And you can tell they're entangled because they have a unique color. So by the early 70s, people were aware of Bell's work, but that was just a matter of good luck, because as you'll see in this paragraph, Bell wrote a paper in 1964 about his rereading of the EPR paper, and he sent the paper in for publication. Now, even under the best circumstances, very few people would have seen his paper that suggested a way to test quantum mechanics in a laboratory, because it was a topic that very few scientists worried about. But what was even worse is Bell submitted his paper while working at one institution, and while it was being reviewed, he moved to another institution. And so when letters were sent to him asking him to make editorial changes and so forth, he never saw those because they were in a pile of lost mail at the place that he originally worked. It wasn't until 2 years later that all this got worked out. And by 1964 or 66, his paper finally was published in a relatively minor journal. And it was only by accident that John Clauser, who was a graduate student at the time, saw the paper and understood its significance. And once Clauser finished his education, he got a position as a researcher. And this is when he approached his managers and said, I'd like to do the experiment that Bell has proposed. And they said, we're not paying for that, but there is a warehouse and it's full of junk. Maybe you can figure out how to build the experiment, but don't ask us for any money. So Bell continued to write on this topic, eventually became more and more recognized, and Clauser and Friedman began to do experiments using junk that were thrown away. Here's a version of the experiment you can buy now. Let me get you to, here's a laptop computer. It gives you a sense of scale. So this is what we call an optical bench, about 6 feet, a square, 6 feet. Here's a laser that produces ultraviolet light. And right there, let's zoom in on that. Right there, we have this BBO crystal. You can buy these little things. You can buy them from Amazon. They cost about $100. And what this is showing is that a pulse of light from this laser goes through a couple of lenses and hits the crystal, which looks like a little chunk of salt. And that produces a photon that goes to Bob and another photon that goes to Alice. And these are entangled photons. Whatever Bob measures is correlated with what Alice measures. So here's the path. The light on this path gets into this fiber, and some equipment here I'll briefly discuss in a few minutes, does some stuff and goes into an analyzer, and this is Bob's experiment. And Alice has the same, this and this are identical. Alice has the same kind of stuff. And there's a computer and a bunch of stuff that modern students know about. And you can do the experiment that Bell suggested. So the Friedman and Clauser effort is called first generation Bell experiments. And by first generation, we are acknowledging that the early experiments done by Clauser and Friedman had what are called loopholes. They had defects that had to be overcome to convince everybody that the experiments were being done correctly. So what are some of the loopholes? Well, one problem in the early 70s is what are now these detectors, these detectors that are common and are essentially 100% efficient. They were far from efficient back in the old days. Occasionally, some of the photons that went to Bob would arrive at a detector and not get seen. Or sometimes nothing was coming to the detector and the detector announced that it had detected something. A false positive could occur. So we had the original first generation experiments had efficiency problems. Nowadays, that's pretty much a thing of the past. The detectors are very, very efficient. Then there's the issue of locality. The experiment done by Clauser, I think I have a picture in this chapter, was done in a laboratory where from one side, from Alice's side to Bob's side, is like a distance of 12 feet. So there was plenty of opportunity. A critic could argue there's plenty of opportunity for some secret signal to go from Bob's equipment to Alice's equipment at the speed of light, so that when Bob looks at his result, he discovers that it's correlated with Alice's result, but that correlation could have been a result of signals that were conveyed from one side of the experiment to the other. And you had to have a way to overcome that. And the way to do it is to make the experiments really big. And by the 1990s, that's what happened, because if for a large experiment, the flight time of light, which is the fastest known way to send a signal, could not have made the trip in time to influence Alice's particle because of Bob's result. So this is another loophole that Clauser and Friedman could not deal with. They had all their equipment was in one tiny little room. Then there's this issue of what is the influence of the decisions made by the experimenters in designing the experiment? And it becomes a philosophical thing. Is it possible that we don't have free will? And if you read the physics literature, you'll see lots of debate about the concept of free will, that maybe we're all just robots behaving because of the initial configuration of the universe, and everything that we think we're choosing to do is just the result of what's gone before. It's the result of what our parents decided to do and their parents, and it goes all the way back to the beginning, the Big Bang. So if humans are involved, there are questions of free will. And there are additional concerns about loopholes. So the first generation could not resolve. They acknowledged these weaknesses in the experiment, but there were no methods for overcoming the loopholes. Remember, this is 50 years ago, in the early 1970s. Eventually came more advances and the second generation tests. And I'm going to show you results. In 1982, Alan Aspect, frequently people pronounce his name as Aspect, but I believe he's French. I think it's Aspect. In 1972, he overcame virtually all of the loopholes and showed that quantum mechanics is a non-local science, that entangled particles somehow are connected in a way that is not consistent with anything we know of in the physical world we live in, the world of trees and stars and so forth. That was the first modern experiment. And it was based on the ability to produce pairs of entangled particles and analyze them so quickly that this locality loophole was overcome, that the efficiency was so high that this was overcome. And you can go through each of these things and see that Aspect and his colleagues managed to set aside all those loopholes and show consistent results. I'll show you in a second. What's more, because of advances in understanding crystal physics, experiments then became possible in the late 80s to have more than 2 particles entangled, namely 3 particles entangled. And the intriguing thing about this is Well, let me tell you, when the Aspace experiments are conducted, many pairs of entangled particles have to be used to produce results so that you can have a table like this, so you can investigate correlation. But when you have 3 entangled particles, you only need to do the experiment once. And the information you get from any one of the 3 entangled particles instantly tells you what the result has to be for the other 2. And the world record for entanglement now, I think, is 8 or 10. It's a huge number. We now know how to, in a single instance, produce essentially a dozen entangled particles, and they all are connected by that invisible connection that we know is true, but we can't explain. The other thing that was a giant leap forward was when Clauser and Friedman were doing their work to create a database, a correlation database, big enough so that you could determine if quantum physics was behaving the way the equations predict. It took hundreds of hours. Nowadays, you can reproduce what took them weeks in an hour and a half. So everything is easier now. And in fact, Clauser, there he is. This is the first paper on the subject with Friedman. Aspace and Zeilinger won the Nobel Prize in 2022 for their advance in the experimental test of Bell's theorem about how quantum mechanics works. Here's John Bell sketching on a blackboard, and this is one of the experiments. If you take a look here, there's a photon source that produces a photon going to the left and another one going to the right, and then some devices used for detection. And this is Bell's theorem. Now, let me show you some real results. This is Aspace's result, 1982. Quantum mechanics predicts, and there's some things that change in the experiment. While the experiment's underway, you change the orientation of some things. We don't have to get into the details. If you're interested in the details, there's a description of it in the book. But here's what's important about this drawing. As we rotate a part of the experiment between 0 and 90 degrees, quantum mechanics says all the results should lie on this solid line. And the actual data are these dots. And this box where the signal exceeds this, comes out of this white area, this is what Bell predicted. This is called Bell's inequality. He predicted that for certain angles, we should get results that indicate that there's non-locality in quantum mechanics. So he predicted this, and sure enough, there are the results. So his prediction started with his first paper in 1962, and by the late 70s, he was predicting these kinds of results. And this is exactly what Zeilinger got. The general consensus is that if John Bell had not died at a very young age, he would have won a Nobel Prize. Almost no question about it. But this collection of data in this box and this box show violation, that's the terminology that is used, violation of Bell's inequality, which means that quantum mechanics is a non-local phenomenon. Here's, these are a little out of order. This one is from 1982. Here's the original Clauser and Friedman paper again, quantum mechanics predicts this curve, and Friedman and Clauser got these data points. But their work, as I say here, suffered from loopholes. Let's 1970, so that's 1972. In 1976, an experiment was done using not photons, but protons. Bell's result says if your results don't lie on this orange line, then quantum mechanics, which quantum mechanics is the black line, that if your data lie along the black line, then quantum mechanics is a non-local phenomena. That is, entanglement between quantum particles is not bound by relativity, but there's some connection between those particles. You just don't know why the subatomic world behaves that way. So that's 1976 using protons. So we have photons, protons. Here's a similar result. Quantum mechanics predicts this curve. And you see the data. These are now photons in 2007. These results agree with quantum mechanics. And the dotted line is Bell's inequality. Anything that is on this side of this dotted line tells us that quantum mechanics, the formalism of quantum mechanics, properly predicts the way nature is going to behave. Here's yet another result. And this is very different. This is a result from a group that is working on quantum computers, and they're not working with light that you or I can see. They're working with microwaves, radio waves essentially. And here's this horizontal line here is the boundary of Bell's inequality. And you see this group of atoms here, there they are, and I've magnified it so you can see. All these data points here tell us that quantum mechanics is behaving in a non-local, that is, a way that ignores relativity. That's why, remember earlier, I said, if Einstein had lived to see this, let me get it back here. There's a quote that says, this result, oh yeah, here it is, right there. If Einstein had lived past 1955, when he died, he would have seen that the world is configured in a way that he would have liked least. If we think back to the EPR paper, what were the complaints that Einstein and his colleagues had? They said, the implication is from quantum mechanics that entangled particles are somehow in communication, no matter how far apart they are. They could be on opposite sides of the universe. And you could do that experiment. If we had the technical know-how, we could send Bob off in a spaceship in one direction and Alice go the other direction, and then send them pairs of entangled particles and say, keep your results. And when you come back together, you can check for correlation. And we have every confidence that correlation would exist. To do the experiment right, you would send them 1 billion light years apart, but that would take another 1 billion years for them to get together. And that doesn't seem very practical. But experiments have been done where the two experiment stations are very far apart indeed. So what we have at this point is that entangled systems, which means that a single wave function describes the two particles, If you know that wave function, you know everything about the components of the system. So Leonard Susskind says it this way. An entangled state, that is the wave function of a pair of or multiple entangled particles, is completely described by a single wave function. But nothing is known about what the individual particles are doing. It's hard to find an analogy in our world. One possibility is we're in the middle of the baseball playoffs. If a baseball player hits a home run, an entity we call the ball ends up in the crowd. But we know nothing about the atoms in the ball. The only thing we can see is the result of the integrated entity. In the case of baseball, it's the ball. In the case of quantum mechanics, it's the wave function that describes the entangled system. And I've already pointed out that people are now doing 3-particle experiments. And in all the experiments, correlation exists no matter how far apart the objects are. So I finished a little early. Let's see, how should we deal with this? So let's do a summary before we decide how to proceed, because this rarely happens. I usually have to hurry to finish on time. So in the prior 3 lectures, we talked about these properties of quantum mechanics. The evidence for wave-particle duality, and a bunch of non-intuitive properties of the quantum world. Spontaneous events, meaning no cause and effect. The properties of entanglement. Non-locality, meaning quantum mechanics does not respect the rules of relativity when it comes to measuring properties of entangled particles. The Solvay Conference, 1927, is where the beginning of people thinking deeply about what is really going on. What is the reality that quantum mechanics conveys to us? That's an unanswered question. And in lecture 6, we'll get into that in more detail. I will show you examples of the various ideas people have. But one thing we have to take note of is, if you have an explanation for what quantum mechanics is doing, what's the reality of quantum mechanics, you have to have a corresponding theory that engages all of these properties: wave functions, the uncertainty principle, the exclusion principle that lets us build the periodic table and explain all of chemistry. All of that, you have to be able to say that your theory for what is actually happening in the microscopic world is the right way to think about it. Again, Niels Bohr said, we don't need to worry about that. It's a distraction. And surveys are done all the time at physics conferences. In fact, I think in lecture 6, I have the example results of a survey done very recently, within, I think, a year ago, where there were 300 physicists at a conference, and they all filled out questionnaires about, do they embrace Niels Bohr, the Niels Bohr approach of don't worry about what's going on there. The the physicist David Merman years ago coined the following, that students are taught to shut up and calculate. If they are like John Bell and keep pestering the professor for the reason why the quantum world is the way it is, they are advised to shut up and calculate. When one of the Nobel Prize winners, I think Zeilinger, when he went to talk about the issue of what the reality of quantum mechanics is, he went to John Bell and said, I want to focus on that in my physics career. And John Bell said to John Bell, do you think I should do that? Because there are many unanswered questions. And John Bell said, I have one question for you. Do you have a permanent assignment? Meaning, if you go explore this field of physics, people are not going to take you seriously until you come up with results. And if you have funding now that is not permanent, you will be quickly disposed of. This has been an issue all the way along. Those few people who wanted to study what is called the foundations of quantum mechanics, that is what is the reality of the dynamic of the physics that's going on, many of them were advised, don't do that. There's an example in the introduction of my book. There's an example of one of the famous professors. He's now a famous professor. When he was a student at Rockefeller University, he told his professor that he was going to study the foundations of quantum mechanics. That is, what is the reality of what's going on? And the professor said, no, you're not. I'm going to give you a PhD thesis topic, and you're going to do that. And when you graduate, you can do whatever you want. And so he suffered through a tedious mathematical thing for 3 years to produce his PhD thesis. And once he graduated, he managed to get a job in a philosophy department, not in a physics department, because he wanted to study the foundations of quantum mechanics. So, and the debate goes on, and as I say in lecture 6, I will show you some of the strategies that people have for what is really happening. And there's a cottage industry in people writing books about what is quantum mechanics really about. And so, and no progress has been made. If you go back and look at the questions that Einstein, Podolsky, and Rosen asked have been resolved because they can be addressed with experiments. And we saw the experiment results right here. All these results would have horrified Einstein. Now, this is the Nobel Prize winning result from Alan Aspect. Now, one thing I can describe, we have about 10 minutes left, and that is the one of the loopholes that's very interesting is this free will loophole. And this has to do, of course, with, is it the predisposed approach of the experimenters that results in the correlation that is seen in these experiments. And so what the group in Zeilinger's group, he's here in Vienna, his group set up the following experiment. They do this experiment, which is controlled by this computer. The computer decides when this laser produces a pulse of blue light so that these entangled photons are created, and the computer decides the orientation of these pieces of equipment so that you can fill up the data archive you need. This particular drawing shows a version of this called the Big Bell test, where this computer is not making the decisions. The decisions of when to create the photons and how to orient the various pieces of equipment is done through the use of a computer game. A student designed a computer game, which is, I have never played it, but apparently it's fun to play. Hundreds of thousands of people use the game. And unbeknownst to them, their choices in playing the game make the decision about how to configure this experiment. So no one person is running the experiment. It's the average result of hundreds of thousands of people that determines how the experiment is configured, and still we get the results that I showed you before. A further extension of this is that the computer that configures the system doesn't come from a single professor or his students. It comes from starlight, light that was emitted thousands or millions of years ago. And the way they do this is they have telescopes, one looking at a star over here and one looking at a star over there. And depending on the properties of the starlight, this computer is compelled to configure the experiment based on light that has been traveling for thousands of years. And that's the kind of extremes that people have to go to convince the community that there's no free will associated with the experiments. So I'm out of things to talk about today. I'll tell you that next time we're going to look at modern versions of these experiments. Remember, all these experiments were done in the 70s and 80s. There are some, let's take a look at this. Yeah. Here's a result from 2023, but most of the results that really startled the physics community were done 20 years ago. Next week, we're going to talk about really modern experiments and how they've progressed to the point where even more subtle effects are seen. So with that, I would invite you, if you have questions, let me see, do we have questions? We have a question. Whoops, get that out of the way. Warren wants to know, have experiments done to eliminate the influence of gravitational forces on entanglement? The answer is yes. Let me describe that. Experiments have been done using satellites. So the way the experiment works is the part of the experiment that, let's pull this up again. The part of the experiment, this business right here, is on a spacecraft. And a photon, a series of photons are sent to the spacecraft, and this part of it is randomly reoriented, and the light is relayed down to another spot on Earth. And that data is correlated with the data created in the laboratory where the entangled particles were created. So the influence of gravity, let's bring your question back up again. The influence of gravity is the spacecraft is in a zero gravity environment, and it's free falling as it orbits Earth. And we get correlations just like you would expect, just like the ones that I'm showing here. And we get the same kind of results when we do everything in the same laboratory where all the gravitational forces are the same for all parts of the experiment. So no, this is not a loophole. And all kinds of other, I mean, these experiments have been reproduced 100 different ways. And so far, there's no contrary evidence concerning the ability of the entangled quantum particles to reach across space and insist on correlation. One thing I hope you'll take from this is we don't say that there is a force. Let's go back to the cartoon of Alice and Bob. Here it is. We have to be very careful not to say that Bob's result forces Alice's particle to behave a certain way, because she may be so far away that no signal from Bob could ever get to her before she records her results. So it's not like he waves and says, he puts his thumb up or down and somehow tells Alice what result she should get. That's not what's going on. The best way to describe it is there's an unexplained correlation in the results. That's why you'll see this word, correlation, over and over again in my book. And I've been very careful. If you see me using language that suggests that there's some physical influence from Bob on Alice, let me know and I will correct that. Because as far as we know, there is no such thing. The question is, why does the world work that way? And there's no good answer. All right. Let's see. Is there anything else I could point to? There's a discussion of entanglement here. There are some references. Some are digestible, some are not. And either in this chapter, or apparently not, in the next chapter, I have a list of the universities where students, undergraduates, you don't even have to be a graduate student to do this kind of stuff anymore. It's so straightforward to do this that, like I said, you could probably build this experiment for under $50,000. And most universities have this. There's, as I say, there's a list at the end of one of the chapters of, if you have a child or a grandchild who's interested in this topic, go look at that. University of Portland in Oregon has an undergraduate program for students who want to do these experiments and try to digest the bizarre ideas that come from quantum mechanics. Okay. Keep asking questions and I'll try to answer them. But I'll see you next week for chapter 5, modern experiments and the crazy results they produce. Okay.
Ken had a good question in the chat about if you have more than two particles. Can you address that one?
Oh, there's something in
the chat.
Where'd the chat go? There he is. Oh. Nope. Hang on. How do we see entanglement with more than two particles? Ah, there must be more to up and down. Yes and no. Here's the way to think about it. We have a minute left to do this. Electrons have two possible orientations. Other particles can have three or more orientations. So, and the rule is this: the spin has to be, the extremes of spin have to be different by a single unit. So an electron has a spin of 1/2, and 1/2 can be up or down, but the difference is 1. Other particles can have a spin of 1, which means they have possible orientations of 1, 0, and -1. So indeed, there is more than up or down. There's multiple different. In fact, I'll tell you what, I'm going to make a note to describe the particles that are involved in GHZ. That's the initials of 3 experimenters who found a way to produce 3 entangled particles. And next time, I will explain what I find. But yes, good question, and I don't know the answer right now, except that I'm guessing the particles that are produced in their experiments have a spin of 1, which means it could be 1, 0, or -1. Okay, thanks for sticking with me. I know this is weird and crazy, but we'll get through it together. Okay? Good day.